Okay, this is lecture 18 about invariant maximality derivations by Harvey Friedman. Please.
Thank you. Okay, so I really want to wrap this central part of the uh, book, in particular this chapter on derivations. I want to wrap it up next week. I didn't get as far as I wanted to for this week because there were some things I tried to do that require certain that would require certain developments in partition calculus that I thought were standard, and I'm writing uh, some experts in it. The first round hadn't heard anything about this. I think what I want is known, and I may be able to use it, but it's not essential. So. Um, let's orient ourselves here again, because I keep changing, making small changes. I didn't put up anything additional uh, on the website. There is a version of the derivation section all the way up to 3.8.2. Uh, I think some of that latter stuff has been reworked. Uh, but I expect everything to be wrapped up next week with regard to the central part. Uh, so let's go over where we are. First of all, um, the book's title has been the same for a little while. Invariant maximality, finite free choice, and finite games, where this is the explicitly pi 0 1 part of the book. Um, the chapters look like this. They haven't changed much. First of all, I got to do some typos here. Oh, no, I meant this reversal. Uh, so I mean, a long time ago we did this, although it has been there has been some upgrading of it. That's the core mathematics. Uh, there's no maximality in here. This is just pure invariance. Uh, this we did, that's the reversal, and this we're doing now. This is to happen. All right. So the table of contents has changed a little bit. Uh, we already did this basic stuff. Um, Usability. There's the usability, the primary or full usability that uses order constraints. This is all review. And that's what we do for the whole chapter now. But there are these ones that are weaker that are for certain kinds of mathematicians. Um, and these are here. You look for a maximal square, a invariant maximal square, an invariant maximal root, an invariant maximal ordered square, an invariant emulator, an invariant free set, an invariant clique, invariant independent sets. These don't obviously imply the master one being uh, uh, order constraints. That's the one that using that implies all the others, but not necessarily the other way. Although we know it does imply when you pass through the reversals. The reversals say that everything and the kitchen sink are the equivalent. All right, so and K usability just means that for dimension K, you have the statement holds for dimension K for the particular function. when the dimension's fixed, it's called K-usable. One usable has turned out to be easily handled, is not an interesting subject. I mean, it's a very simple subject that can be dispensed with easily. This was some mathematical things. This we're going to use today. This says that usability doesn't change under isomorphisms and under certain when you change the function sum, it's usable if and only if it was originally usable. That's what stability of usability means. Usability, in fact, K usability. Yeah, full K usability. Full usability means for all K, you have full K usability. And full means that we're only talking about the order constraints, was the strongest form. Now, this is an intricate section that we covered, namely the complete analysis of which finite functions are usable, are fully usable, fully usable, fully two usable, turn out to be all the same. Everything's the same there, except when you get down to one usable. If you're down to one dimension, then things are different and they're relatively trivial and special. All right. And one usability has been completely analyzed, no matter whether the function is infinite or finite. All right, then we got into infinite usability. That means that we're talking about usability of a function that's infinite, i.e. infinite domain. And then, of course, that's where the connections with set theory come in. And so we only do some very simple ones. An almost identity is an identity together with a finite function. Oh, by the way, the overriding necessary condition for any kind of usability, except the one usability, two usability and above, the overriding necessary condition is that the function is strictly increasing. And now section 3.8 is the red meat of the chapter, although there are important things to come. This is nothing because this was already done. This is just a notation for a particular finite function. Now, I've reworked everything, and so we're going to start from section 382, and we're going to go through 382 to 384, and that's still all within Zermelo set theory. You see, this is all within well within ZFC. In fact, even it's even you can even use just Zermelo for this. This is the iterated exponential of the exponential of the power of the 2 to the x function. Yeah. Yeah. Now, what we did last time, what we've done already fairly carefully is how to use omega 1, but that doesn't have enough machinery to handle all the things I want to do. But all this machinery, might be confusing. So I even have a special section where I go back and just do the one for omega 1 and strip everything clean. Don't use the master construction in any kind of generality, at least. Strip this thing clean so it works for this omega 1. In fact, you can suck out some more information if you're just going to use omega 1. You can do some things. So we're going to do the 2 through 4, and then next time, the plan is, that is the third time on this, the plan is to get right into the full proof using large cardinals, using subtle cardinals. Actually, I wanted to change the notation for this. Yeah. This is where we use the the large cardinal hierarchy to prove stuff. And so I'll do this in full detail, polished detail, using the master constructions that we'll talk about today. Um, and then talk some about how you use con instead of WK. In other words, make some formal conclusions about what's provable and what here. Uh, and then I think we'll move on to some additional results. Eventually, we'll want to get to some additional results where we actually deal with more general functions. But this is a good playground right here. And also, a lot of open questions will arise when we do that. We eventually want to do this. We want to show everything's equivalent because one of the statements it's actually not actually this is a little bit wrong. I'm doing many equivalents. Let me say it differently here. Yeah, because one of the ones in here is the one that we actually reverse. The one that we reverse is among these. Okay. Yeah, I overstated this. This is equivalence with K equals N. Just about everything that we feature in here is equivalent to when you have K equals N, and that's needed to justify why our reversal is taking care of everything we want. So in other words, the reversal shows that everything in here that we're talking about, every serious thing in here that we're talking about with K arbitrary, uh, is equivalent to con SRP. Okay. All right. So that's the schedule, so to speak. All right. So let's get into this master construction. These are the critical constructions, and I want to be specific about what base theory I'm using. So I'm going to use the base theory ZFC minus power set. Now later when we discuss this, you see Zumelo does not cover ZFC minus power set. Zumelo is much stronger, but it doesn't have replacement, whereas this does. And having replacement is the most convenient place to simply do these things without being careful logically. And then we fix things up later in terms of using other base theories than this. But officially, the master constructions in here. And we're going to use these master constructions. Actually, we're going to use them, this master constructions, I think, in here at least. Yeah. In other words, next week also. First. Now, these constructions are used to convert combinatorial set theory into full usability results. In other words, we have a bit of a machine here. We have this combinatorial set theory, and we want to get usability, right? That's what the point of the highlight of this derivation chapter is. Combinatorial set theory gives full usability of things, but there's a machine that you need in order to make this conversion. And that machine is this master construction. That's the way you should look at it. And in the master constructions, we fix an uncountable regular cardinal kappa. Now, of course, ZFC minus power set doesn't even prove that kappa exists. Omega 1, of course, being the least one. Uh, but that's not the point. The point is we just want this as a placeholder because we're going to apply this to various kappa. The kappa, the so-called Beth numbers, the iterates of the power of 2 function on omega, and also we're going to use it on omega 1. Well, we did some of that. We're also going to use it when kappa is certain large cardinals. And we just use this master construction to do our stuff. Yeah, sections 3 through 5, we work in ZFC minus power set with kappa exists for various uncountable regular cardinals. Kappa, okay. So kappa is a fixed uncountable regular cardinal. And then we have these spaces. Now, a lot of this is stuff we did already, but I had to polish it up and integrate it and, set it up right and so forth, reset it. It was very time consuming. Uh, all right, so we have these spaces T alpha, which is alpha plus 1 cross 0, 1. So you see that there's two coordinates of the points. You see, it actually turns out to be important that there be a top point here. So alpha is the top point, right? All these spaces are infinite because even if alpha is 0, we have singleton 0 cross 0, 1. And the convention has been for some time that this is the rationals in 0, 1. All numbers are rationals. All right, and then we define this ordering, but I want to put subscripts to make sure that one's dependent. This definition is not dependent on kappa, so kappa will not appear. But some later definitions, kappa does appear because the definition is dependent on the choice of kappa, but here it isn't. Although we only care about alpha less than or equal to kappa. So this is the lexicographic ordering on T alpha, which is the obvious one. And that's dense, okay. And then we have the restriction notion that we use a lot. Well, maybe we use it properly. Let's actually talk about it properly. How about this? This better, right? Okay. Now we needed to fix the effective enumeration of these rationals. And it's important that we also have a second, totally different, quite different kind of linear ordering on T alpha, uh, which is given as follows. It's lexicographic, but we use the subscripts on the second coordinate, and we use I less than j. So you see that this is a well ordering, right? This is different. This is a well ordering. This other one isn't. All right. This time I did it right. Yeah, the restriction notion. All right. Now it's important also to extend this ordering to k-tuples. And we do that a kind of lex max or max lex. Max lex. Yeah, because first by max and then by lex. Right? In other words, you First determine who's got the bigger max under the unary case. If it's smaller, then you're done. If they're equal, then you go lexicographically. Okay, and then we have this restriction notion, which was butchered a little bit. Here we are. And now, uh, yeah, so I also want to use restriction more broadly. This comes up, I want to use restriction more broadly because if you take a substructure of a structure, you usually don't want to keep writing what you're restricting it to. And I'm not that happy with the convention that you're just intersecting. So I just use restriction flat out. Did I actually? I don't know if it appeared in this version. Let's see. No, it's not here. All right. We'll cross that bridge when it comes. I'll show you what I mean. In other words, you write like R restricted, and you don't even say what it's restricted to. If you're in the context of a structure, it just means you're restricting to the domain of the structure. That's all. It's just an obvious convention. All right. Now this just summarizes basic properties. This is a dense linear ordering. This is a well ordering. It tells you what the endpoints left and right are. And this is good in order to have confidence that you actually know how these definitions work and what they mean, what these constructions mean. All right. Now we already know what we've been using order invariance in the rationals all the time. And if you have this, then there's the canonical lifting of it to you might as well do it to just kappa. There's nothing too much to be gained by doing this, restricting this to E alpha star. So we have E kappa star is the lifting from E. In other words, E is order invariant. This is going to be order invariant with respect to less than star. Now, here is the crucial definition. This is the important greedy construction. This is vital. And the greedy construction depends on the order invariant set you're starting with and the ordinal kappa that you're picking. So this really does depend on kappa. And we won't define SE comma alpha. We'll just rely on restriction notion. So SE kappa is defined by transfinite recursion. So a point gets in the set if and only if when we restrict to everything below, if we tack it on, we get something contained in E kappa star. You could think of being contained in E kappa star as satisfying a constraint, right? So it says that you put something in this set if and only if you can get away with, given what you previously put in, in this new candidate still obeys the constraint. And this is the so-called greedy definition, right? Let's see, do I have to actually say what X? Let's see, so X is in there if and only restricted. Now you know that in order to put it in there, X has to be decent because it's got to be part of E kappa. This has got to be part of E kappa star, which means that it's got to be in uh, T kappa, right? T kappa K. Yes, this is okay. So S is unique and it's maximal among all the subsets of T kappa K with this property. The Cartesian power is contained in EK. Remember, EK is is dimension K times R. And this is dimension K, so the dimensions are matching nicely. All right, and this is just proved by the usual way you justify definitions by transfinite recursion, because you first of all you argue that it's unique if it exists. You define what you mean by partial solutions, and then you prove the partial solutions exist by transfinite induction. Okay, so this is straightforward. And also, greedy is stronger than maximal, by the way. But among the but it's important to know that if it's greedy, it is maximal. And now we have a definition that depends on kappa. This is a juicy kind of set. It's the set of all alpha such that for all K and R in order invariant, for all order invariant E, this means it's contained in. This is inclusion. We have that that a certain thing is a substructure. We're gonna take both these less thans in here, and we're also going to use S. Right? And this S is the greedy set. So we're going to take the whole greedy construction, and that forms a structure, but it's on only, we're looking at the alphas for which this, see, alpha cross 0, 1 union K 0, kappa 0. If alpha is kappa, this is just the space, the full space, T kappa. And everything is big and everything. And that's what we have here. See, if kappa is equal to alpha, that's what we have. We have the real thing here. And we're just saying that we're looking at the alphas for which when you cut everything down, at least you cut this part down. You have to keep this because otherwise it can't be an elementary substructure. See, this kappa 0 is said to be the greatest element in this order, is said to be the right endpoint of this ordering. This one here. And so an elementary substructure has got to have kappa 0 in it, of course. But it could, well, what else does it have? Well, since kappa is an uncountable regular cardinal, we can force this to be a no gap. This means no gap. This is exactly what no gap means when you take the elementary substructures. And this set is well defined and is a closed unbounded subset of kappa consisting of limit ordinals, right? You have to prove this. And the cardinality is kappa, regular cardinal. Yeah. Okay, this is straightforward, and this has been done in many contexts in model theory, particularly, but I think set theory and model theory. you make the elementary substructure, but that has gaps in it. And then you fill the gaps in and then and take an elementary substructure with those gaps at least taken care of. Maybe you create new gaps. And you keep doing this and you take the union, and that's how you get it. And you're going to use regularity uh, in order to pull this off. You're going to use that kappa is regular. Oh, and cofinality bigger than zero. Yeah, you need regular and uncountable regular. Sorry, uncountable regular is what you need for this. All right, now we need the notation. Lambda of alpha kappa is the alpha element of K kappa. Yeah. Now we really care about alpha, but we also have to say that this is with reference to kappa, right? Whole construction. Because I could start with a different kappa and I could wind up with different lambda alpha kappas. Okay. All right, now we define an embedding. Now all of this is going to be a very special situation related to Gödel's collapsing lemma work that he used to prove the continuum hypothesis holds an L. That's kind of the point of contact. But this is a very pristine form of it that's focused on one particular point, which is that we have this top point, kappa zero. All right. So we have this embedding function, which goes from T alpha to T beta, which is the identity here, and maps alpha zero to beta zero. Maps top point to top point. Okay, now we need to prove that if you have if you go from one, so think of these lambda alphas as so-called indiscernibles. These are like indiscernibles. If you have a mapping from an indiscernible to kappa, one of these pi functions, which is just a simple function, is the identity and changes at one point. That this is an isomorphism between the original structure and this particular structure, this time with the restriction signs. Here we don't need restriction signs because we define this carefully like that. Here we want to restrict them because we have a gap in here. Now it's obvious this is an isomorphism from here onto something, but I'm claiming that we don't change I'm claiming that it's still the S function. I mean, it's still the S set. It's still the greedy set. Okay, and the reason is that we have elementary equivalence with a structure that says that this is the greedy construction because that's first order involving this. You see. So because it's the greedy one, you can show that the image under this embedding has got to be the real thing. All right. And then from that, you see you have alpha goes to kappa nicely, lambda alpha goes to kappa nicely. And since lambda beta goes to kappa nicely, because beta is just another alpha, then alpha goes to beta nicely by just composing and with the inverse. So you get that let's make this a little prettier. So I didn't have time to format everything. No, I don't need the kappas for this. Yeah, that's a mistake. Yeah, right. Don't have to restrict. The kappa is needed to tell you which lambda this is. Kappa is needed to tell you what the greedy construction, what the greedy set is. Each kappa. Okay. Make this nicer here. Right. Okay. Okay, this is just review. This is nothing new, but I wanted to record it. This is nothing new. And this thing here comes from this lemma. Okay. Now, this is very important for showing, for reducing the cardinals that are needed to prove things. This is, uh, uh, in essence, you'll see that this means that the maximum of tuples don't count. If you change, if you have indiscernible, if the maximum indiscernible, if the maximum of a tuple is an indiscernible, you can move it to another one. That's what this is more or less saying. Now, in order to apply this, we cut this back down to the basics. So we just unravel things. So we have an order invariant set E, and we have these two ordinals, alpha and beta. Then if I have points in the space less than or equal to now the lambda alpha kappa lambda alpha, but kappa is needed because of the construction dependent upon kappa, if you remember. Okay, comma 0. Then and I have then this is in the language of our usability notion. If you remember uh, the way usability works for these particular functions that we're working with. Okay, so if I have these, and the idea is that's the idea, and then it becomes this is all, but however, this is in the transfinite. So and I replace each lambda alpha kappa 0 by lambda beta kappa 0. I'm not doing simultaneous replacements. I'm just replacing one. I'm just replacing uh, uh, the highest one. If I replace alpha kappa 0 by lambda beta kappa 0, any other one, then uh, the result membership in the greedy set remains the same. All right. And that can be proved from the earlier thing. And then this is just regurgitation of the same claim of maximality for the greedy construction. You have maximality. All right. This is from the previous statement. All right. Now for some pep talk. Note that this theorem is just the kind of maximality we are looking for when we invariant maximality. Yeah, that's what I want to say. is the just the kind of invariant maximality we're looking for when we verify usability and its simplifications, which is what we're doing now, but has only a very restricted kind of invariance. You see, namely, we are only saying that a single indiscernible can be moved. Now, what we really need to get is that several indiscernibles, a tail of indiscernibles can be moved, and that is where the combinatorial set theory is needed. So moving a single indiscernible helps, but to move multiple indiscernibles requires various combinatorial lemmas, some of which are not available in the ZFC. All right, so now we're ready to prove usability. You know, this is K usability. Either you put colon K in here or you just say K usability. This is just a variant of notation. Actually, this is not the actual official title. Did I use? I might have used. Let me see what I used for the official title. Be curious. No, I used the okay. And this was a mistake. I didn't mean that. Yeah, we dodged the notational issue here. All right, so let's talk about it. Whoops, I got to find out where I am. Yeah. All right. We finished the master construction. The master construction is this chain of elementary substructures or CUB set with respect to the greedy construction, the greedy construction and its elementary substructures, so to speak. And we have a certain low-level kind of indiscernibility going on there. Namely, you can move one indiscernible, the top indiscernible. All right. Now we're ready to actually uh, prove some usability. We actually prove this is fully K-usable. Now, here's where I remember I said that the master construction is used to convert combinatorial set theory into usability. So now where is the combinatorial set theory I need to do this usability? Well, it's the Erdős-Radó theorem. And this is the classical setup. Mu is the infinite cardinal, and we inductively define the iterated exponentials. And the theorem is we have a coloring with mu colors of this cardinal, this successor cardinal of x sub n of mu into mu colors, and doing it with the n plus one element subsets, then I can find a homogeneous set of cardinality mu plus that's it. Okay, now this was proved first by Erdős-Radó in 1956. All right, but in order to apply it to our situation, we need to fool a bit with this. So what does it mean to be an order invariant function? Okay, I forgot to put the dimension here. Okay. So I have a k-dimensional set over kappa, uh, a set of k-tuples. Uh, Order equivalent has the obvious meaning. Uh, and we also have order equivalence. We have another notion of order equivalence we're going to use. But the very first thing we're going to do is just use this simple, most basic one. And this one says, this is a weaker one. It says that, actually, I remember that I decided not to use this. Uh, I needed the notion of, yes, I wasn't using this. This has to, this has to, this has to be removed. I do something else. Uh, I define the notion of special set instead. So let's just take this out. All right. So now if I have a function, uh, if I have several functions defined on the less than or equal n plus one element subsets, of arities less than or equal to n plus one, arity zero is never allowed, by the way, then I can make these functions order invariant over some single a of cardinality mu plus. Okay, this is an order invariant form. This is an order invariant form of Erdős-Rodó, and this is easily proved. I mean, it's a little bit messy to write down all the details, but you know, this is a well-known kind of thing, a well-known thing, or well-known kind of thing to everybody, and well-known thing probably. Yeah, actually, probably. All right, so uh, we can go further with this. Actually, this is a mere specialization of this. This is not new. Uh, Namely, we only care now about these particular cardinals. The best numbers over, in other words, the iterates of the power, iterates on omega, but we always take the next cardinal after. And we want to talk about only colorings of size 2 to the omega for our purposes in this subject of invariant maximality. And then this is a trivial special case of this, just changing the notation around. You have to match up the numbers. This has been reduced one. Uh, this is going to be reduced one because it's going to be k minus one to the 2 to the omega to match this. All right. Now, actually, in this work, we will only use that A is infinite to do these things. Okay, and now here's the main notion that we need in order to do this usability that we want. Order equivalent over omega means that whenever two vectors are order equivalent over omega, if they're order equivalent and the places where they're finite are the places where they're less than omega are the same places with the same numbers. And here we need this notion, uh, being order invariant over omega just means that you respect that notion. Okay. Now here's the notion of special. Membership in X of X and D does not depend on max X. Does not depend on max X. In other words, if you change the max by raising it, uh, then you get equivalence. Membership doesn't change. In fact, I'll probably add a formal version of this, but it's pretty clear what I mean. All right, now we have here is the combinatorial lemma that we really need. Here's the right shape. K at least 2. If I have a set of the less than or equal to K tuples in this cardinal that's special, in other words, membership does not depend on the max, then D is order invariant over omega. Yeah, D is order invariant over in the slash omega over some infinite set, right? Okay, so then applying this to something that is sort of like the usability that we want, uh, and remember that breakdown. Remember that this follows immediately from that breakdown of the uh, that we did in the uh, critical constructions or master constructions, if you remember. Uh, this Actually, this thing here, yeah, right. So this thing here involves the greedy construction. Yeah. So this is some combinatorial set theory just applied directly to something that looks like this that we did in the previous section. All right. And this thing has just the shape of the usability we're interested in. Uh, so we get something that has the right shape and that's in the large car that's in the set theoretic context, and then we take a countable substructure, and therefore the domain has to be the rationals with endpoints because it's countable dense. And then we pull it back down to the rationals by taking a countable elementary equivalent substructure of something that looks exactly like what we need uh, uh, for usability of these functions. Uh, See here, result of replacing the elements of A among by its successor, like we did previously when we did the master construction. All right, so that takes care of this one. Right here. Now, it turns out that it's not trivial at all to get the following variant. Instead of using this, we use this. By the way, if that n minus 1 is n, then this requires large cardinals. This requires large cardinals. At least we know it requires large cardinals if k is arbitrary. And that was done with our reversals, with our reversal. But when we stop short of the endpoint, remember the right endpoint is 1. When we stop short of the endpoint, so I think the official title was like this, because I'm talking about k usability. Then this actually is not so straightforwardly follow from what we did earlier, and but it's done by an adaptation, which I'm going to go through very briefly because I'm over time. So, but I think you'll be interested in how I actually do this. Uh, I first prove that this handling this, which is what we just did, is equivalent to handling this 1 over n through n minus 1 over n semicolon n minus 1 over n and 1. This means that that we're talking about invariance with parameters from here instead of parameters from here, parameters from the top interval instead of from the bottom. With these abutting, n minus 1 is see the n minus 1 over n is abutting, just like they were abutting here. And the equivalence between these two comes from the work we did on stability of usability. And this is the definition of what this function is that we're talking about. It's just what you'd expect. Okay. Um, so I claim that the usabilities are the same. The usabilities are the same. These are really two of the same. And this is done by transforming the functions from one to the other by operations that preserve stability, that preserve usability. Uh, yeah, so we start with the one that we want to. Okay, so we have three functions. So I'm not going to go through this too much. But anyways, uh, we have enough stability of usability to actually convert the one to the other using the minus function, uh, which is a reverse isomorphism, and also using isomorphism flat out, and also inverse. Usability is preserved under inverse, under isomorphic copies, under isomorphism, and under minus, where you minus the domain and the range at the same time. That's how that works. And now, in order to, I think I just have time to talk about the strategy. Now, in order to remember what in order to get this in order to get the usability of this altered function, remember this one here. Sorry, this one here. We're trying to get the usability of this one here. Okay, in order to get this, we make the following modification of what we did earlier. Let me just say it this way. We change the spaces T alpha to T alpha prime by tacking on just an interval. It's not important that it be 0, 1, by just tacking on something on the top that has no left endpoint and a right endpoint. Tack something on at the top. And the ordering, the less than star ordering, is going to be expanded where I put that on the top with its normal order. But the tricky point is that that how do I change uh, the double star relation? Remember, that's supposed to be the double star ordering, that's supposed to be well ordered. Well, now the well ordering relation is going to be, I put the stuff that I put on top, I put in front. I put in front. And I don't put it in front with the usual ordering because that's not well founded. I put it in front based on some enumeration of it of type omega. In other words, I make it of type omega and I stick it on in front. And then I do my double star construction as I did before with the lexicographic ordering and the max lex. I use max lex and all that. So then I can build my greedy, I build an altered greedy construction. I build an altered greedy construction and then try to repeat everything where these modifications don't really uh, affect the inner core of all these of the constructions. Okay. Uh, so I'll have indiscernibles as before, but they'll correspond to these numbers here, and 0, 1 will correspond to this interval up here. Yeah. So actually, I did this way, and I just literally repeated all of the definitions, modified all the definitions in detail, and repeated the arguments, with tiny change with small changes that have to be made, and it's kind of tedious. But now that I think about it, I've been thinking about this a little bit, just the last couple hours. I think I might be able to uh, make a general statement that the uh, infrastructure that we built, the master construction that we built, now modified, is actually closely related. In other words, a lemma that says that you get the same indiscernibles, the same lambda alphas, and also that the uh, greedy sets that I used in this variation are closely related to the greedy sets before. They're not the same, but they're kind of closely interdefinable. So I can save a lot of trouble. I can save the trouble of re-examining arguments and lifting them, showing them that the same arguments work. So I think there's something there that would clarify things. In other words, that I can actually make this smoother. So this takes care of all the stuff in this section 3.8, all of the stuff that is still doable in ZFC. And in fact, everything here is doable in Zermelo. Now I will add a section that strips this clean to its bare bones, where I just use omega 1 and there's no Erdős-Radó. Of course, the results are much weaker. I'm either in dimension 2 or I'm just using two indiscernibles, 0 and 1. The statement just has is just n equals 2, right? Well, depends on how I numbered things, 0 and 1. In other words, 1 is the right endpoint, and 0 is something in the middle. So I will have that section for readers that just want a small dose of this, namely omega 1. I think that's important. But this is the Erdős-Radó section. This takes care of all the stuff in ZFC. Now, the same master construction is going to be used next time with large cardinals. Then you have more combinatorics, and you get stronger usability. I think, okay, Andreas, I'm done now.